Started.
Yep. Here you go, Jeremy.
All right. I want to welcome everyone. This is part 2 of the March 2022 meeting of the Delaware Valley Amateur Astronomers. So I'm Jeremy Carlo, a programs chair. This is, I think, the first time we've ever done a 2-part meeting. So this is a little bit more informal than normal. So welcome to everyone joining us on Zoom and to everyone joining us on YouTube as well. Just had a couple of really quick announcements to get us started. Lou, did you want to tell us a little bit about our plans for the return to the April meeting at Radnor?
Yes. Well, so the very first, most important plan is we went down, we met with the guy who runs the place. This is at the same place we've always met at the Radnor. Oh, hold on a second. You know, we met down at the Radnor. I don't even know what the name of Radnor is. Is it a community center or whatever it is? I've gone there for so many years, I've forgotten the official name.
It's a township building.
The Radnor Township Building. So in either case, we're going to meet in person there, and Jeremy will talk about who our presenter is. But very importantly, we're starting a brand new thing, and that is we're going to simultaneously live cast the meeting. So if you're in person, wonderful. I miss you all. I want to see you all in person. But if you can't join us, you can look at the meeting on YouTube. And it will be happening as the meeting happens. We're going to be live streaming it. Someone's going to be monitoring messages on YouTube, so hopefully there'll be some level of interactivity. And you know, it's a great big experiment for us, but we're really looking forward to it. So that's it for me.
All right, thanks, Lou. Sounds good. So Dick took a really nice picture of an asteroid. Is it NISA or NISA? I don't know if you would be interested in sharing that image. It's currently on the DVAA homepage. And also it's Dick's birthday, I've been told. So please join me in welcoming, giving him a happy birthday.
Happy birthday.
Happy birthday.
Please don't sing, it sounds terrible on Zoom.
Happy birthday to you.
Apparently that sounded pretty good.
Ah, there's Dick.
Let me unmute him.
Yeah, Dick, you're muted.
I'm unmuted. Yeah. That's a good thing I was muted, because you wouldn't have wanted to hear what I was saying about Windows 10. It was nothing nice. I like Windows 7.
Wait till you get 11.
I have 9 Windows 7 machines and 1 Windows 10, and it's going to become Windows X because it's going to be tossed. Anyway, here I am. Oh, you can see me. That's interesting. But there's also another Dick Steinberg in this meeting because I'm confused here. So I'm going to try to close that one. All right, you got one. That's enough. I don't hear anything. So who's
we're all listening to you.
Oh, you're listening to me. Oh, okay.
We hear you fine.
Well, I don't have any more asteroids to show you tonight. Sorry.
All right. All right. Well, if you want to check out the picture, it's on the DVAA homepage.
Oh, how did you handle the GIF part?
Let's take a look at it.
It just worked,
okay.
I think.
I hope it worked.
Yeah, it seems to work. Thanks for letting me do that.
Yeah, that was an amazing night. It was so hazy and whatnot. It's amazing that anything came out. So I zoomed over from that asteroid to the comet that you may have seen also, but I only got, I forget, maybe 20 minutes on the comet. So it only wiggles a little bit. It doesn't actually move. But it was the comet. It was amazing. So the program is a great program, SkyMap Pro, but there was a tremendous bug when they updated it from version, I think it was 11 to 12. They went along with Microsoft's recommendations about security, and they totally changed where the data goes. So I wound up putting in a 20-year-old asteroid, file, asteroid position file that was 20 years old. So of course they were out of place. They were off by a degree or more. Anyway, so I finally got that straightened out, and now it's working great. And the proof of it was I found that the asteroid, it was right where it belonged, and I also found the comet, it was right where it belonged. So it's a great program, SkyMap Pro. Trouble is the Chris Marriott, the guy who wrote it, is he's been sick for a while. I'm not sure exactly the problem, but basically I think he's just old and like me, and he's retired. So the program, even though it's great, it needs a lot of TLC, and I don't think he's able to give it. So, but anyway, in the meantime, it's a great program. I use it all the time, and it's cheap. I think he gets $100 for it, something like that. I highly recommend.
Thanks, Dick.
That's it for me. I'm done spieling.
All right. Did anyone have anything else for the meeting? I don't think anyone had any announcements, but if there's anything else. All right. So let's move on to the main reason why everyone's here tonight. We're very happy to have John Conrad back. So John gave us a presentation last week called Rocket Science 101. I think we all have our diplomas from that. And now we're going to go on to Rocket Science 102, which is operating in space. So please join me in, again, welcoming John Conrad.
Oh, that was fun. Put it
I want
on
to mute
speaker
this.
view, Dick.
Hang on, I want to mute.
He's muted too.
You're muted, John.
And it went away. You hear
Hello,
me now?
John.
Hi. First off, before I put up the slides, I just wanted to say two things. One is, thank God it's not the night of Villanova's, 16th, their round, because I don't know that I'd be looking at any boxes here at this point. But at any rate, the second thing I'll say is I'm glad anybody came back after last week. So thanks for being here, and let's get started. Share the screen. See what you can see. Is that good?
Yes, sir.
Okay. And I want to move this little thing out of the way. All right, folks. Let's see. Jeremy, maybe you know, there's a little band that appears across the screen that says, right across where the slide title is. And this was here last week, and I didn't know what to, oh, there we go. Okay. I figured out a way to get rid of it this week. All right. These smart programs drive you crazy. All right, folks. So we're onward and upward tonight. Rocket Science 102 tonight. And then you will officially, hopefully, consider yourselves experts. This is the opening part of the presentation. Once we have the rocket get our payload in the right direction, we need to know where we're going, and those are orbits, and we're going to talk about orbits for a bit. And then we're going to talk about the spacecraft that gives us the ability to operate up there. And at that point, I talked to you about the very simply stated mission of rocket science overall. We will have covered all three legs of this. And people that I think validly refer to themselves working in the field of rocket scientists or the technical people that work in any of these fields. It's a fairly broad field. Last week we covered this, and so we'll get on with it now and start off with the orbits. Some basics. I think I've got some scientists here in the audience, but pretty much everybody knows that a favorite saying of physicists is that gravity rules. And having walked down from one of the meetings there a couple of years ago and decided to take a shortcut for about 4 or 5 feet of sloped grass, I can tell you for sure that gravity rules. Gravity can be a you-know-what, and we can think of it as it is one of the 4 forces. It's the one of the 4, the other 3 being 2 nuclear forces and the electromagnetism, but it's the one that operates, if you will, at the furthest distance. It's in existence everywhere across the universe, and so let's get on with it and see what we know about it and why it matters to orbits. There's a preeminent scientist we all know, And until he came along and wrote about it late in the 17th century, it was something that had been understood as much as 2 millennia before that, but nobody had figured out a way to really analyze it, model it, and then finally write a universal equation, or I should say the equation of universal gravity. And so Newton did that. And from then on, we all understood that all mass attracts any other mass in its gravitational vicinity. And that's not just true of what most of us think about all the time, things that we can see, but the dark matter, which is on the order of 4 or 5 times as much as the matter that we're able to sense and know about, is there, and it's very much exhibiting the force of gravity because that's how we know about it. So Newton was the one that modeled it, wrote an equation for it, and in order to do that, he had to literally invent a new branch of math, which you're probably aware of as well. One of my favorite things from his treatise of the system of the world, I think around the end of the 1760s, is this picture, which helps you understand orbits fundamentally in a simple way. He said, let's take the Earth, let's go to the top of a tall mountain and put a cannon up there and point it parallel to the ground. And so if he gives it enough energy and fires a cannonball, it gets on what's called a ballistic trajectory and falls back to the Earth at point A. Give it more energy, it gets further, like maybe an intercontinental ballistic missile, and it gets to B when it falls back to Earth. But if you give it just enough energy, you can get it to keep falling back toward Earth, but miss it, like C. And so you go into a circular orbit where the point that it left the Earth is the perigee, closest point, and C is the furthest point. And of course, if it really was circular, then you'd run into mountains all the way. So that's not quite a circle. And so if you give it yet more energy, you get into an elliptical orbit with a much higher apogee. And finally, if you give it enough energy, it'll travel not just falling back to Earth, but escaping Earth's gravitational attraction and going at what's called escape velocity, looking for the next thing to attract it. Kepler, you may know, was actually here first, roughly 50 years before Newton. Johannes Kepler actually first worked for another mathematician, astronomer, Tycho Brahe. And Brahe was an amazing observer and data collector. And he used Kepler actually to help him collect data. And so Kepler inherited his books when Brahe died, I think around the late 1590s or something. And Kepler used all the data about the observations of celestial bodies, especially the planets and our moon. And he came up with 3 laws of planetary motion that we're probably all familiar with. Maybe the principal one in this picture you can see is that all orbits around a much larger central body are circles. Are conic sections, and the case with no eccentricity, in other words, it's not stretched at all, is around one, like C. And once the semi-major axis, the long axis, is longer than the 90 degree to that minor axis, then you have the case of an ellipse, and eventually you get also parabolas and hyperbolas. At any rate, Kepler modeled and defined this. Newton actually provided the math that allowed these things to be represented mathematically. Einstein needs to be mentioned as the third of the great scientists that added to our understanding of gravity, as we know, about 100 years ago, with both the special and then the general theory, which we now understand operates at great distances and much larger scales than anything we worry about for orbital mechanics. But at any rate, we understand it's not just mass, but light that is affected by gravity. And so finally, I'll just say the first two, Newton and Kepler, are pretty much the ones that are behind everything that's been derived and become the field of orbital mechanics, which was very much necessary by the time we started to launch things into ballistic trajectories or orbits. And a simple thing that we can say about orbital mechanics is that it can be represented by a number of different defined parameters. One of the easiest ways to talk about an object that will orbit a much larger object is to define the three axes of the radius vector and the three axes of the velocity vector, which is necessary and sufficient to give you an orbit calculation that you can move forward and backward in time with. There are many other combinations that have been derived. You've heard of, if you aren't in the field, you've probably still heard of eccentricity and inclination and semi-major axis and perhaps argument of perigee and so on. And like I say, if for any object that we observe, we can calculate these, then we can calculate the forward and backward motion with precision. The reason we care about this, besides all of the satellite applications that we're going to talk about, is that it answers some really down-to-earth questions like getting in the car, driving into the city to a restaurant we've never been to. And what we used to do is punch some, not small box on the dashboard. Today, everybody's phone's got one of these in it, and it just tells us where we are and how to get where we want to go. And the other thing that I'm very thankful for is that now we can watch all these literally thousands of things that are near Earth objects in orbits very close to our own around the sun. And we can very accurately calculate and predict, not just for decades, but literally for centuries, whether or not something that looks like it might come close to a collision is actually going to hit at some point. And at the moment, everything we've calculated is at least beyond near scores of years, if you will. Now, we have to do this all the time to update it because things perturb orbits, and something might perturb one of these near-Earth objects and end up with it moving into an orbit that is going to collide with us. So we should be very thankful to be able to calculate this accurately. And I will just observe maybe just a coincidence, or maybe there was cause and effect here, but from the 40s into and through the 50s, we started the space age, which we couldn't have done without each of the three of these. And so it's not just the rockets that we talked about last week and the computers that we know started with ENIAC in Philadelphia. It's also a technique of using the computers that allows us to rapidly calculate orbits, numerical integration. So now we'll just look in an overview at the three classes of most common orbits, and we'll stick around Earth instead of talking about going further afield, partly because 99% of all the satellites launched have been put into Earth orbits, and partly because it would be a little difficult to talk about crossing over areas and stuff. So we've got the obvious three categories of altitude from low to medium to geosynchronous. We'll talk about each of those. The boundaries, just for definition, are 1,200 miles out to get to the top of the LEO band. And then between then and geosynchronous altitude is all medium Earth orbits. And of course, as the distance out goes, the period rises such that the low Earth orbiters are all in periods on the order of 100, 110 minutes, something like that. And geosynchronous, you understand probably already, is a day. The first category, LEOs, is illustrated quite well by this cloud you see not very far above the surface of our sphere. A lot of people think about a satellite like the ISS, which we can see often, and look in the sky, and they picture spatially, if they do this in their mind's eye, something that's way out there. Well, you know, to be only 150 or 200 or 250 miles off the surface of the Earth, which is 8,000 miles across, is very, very different than being way out there when you look at it in perspective. And within those bands out to about 1,000 miles, it says 20,000 objects greater than 4 inches. The Air Force, I think, tracks, catalogs, and predicts the orbits of more than 100,000 objects in near-Earth orbit now, if you count all the smaller things too. It's a pretty crowded place, and with constellations like Starlink and OneWeb, it promises to get even, and I'll use the word worse, from the standpoint of those of us that like to look up into the sky and not see all kinds of shiny things up there. All right, so why is the low Earth orbit so popular? Well, it's pretty obvious. It takes a lot of energy to get a payload off the ground. And if we can get a useful mission out of it by not going very high up, that's the cheapest way to get some value out of an orbit. Also, it is the best place if you're going to turn around and look back at the Earth or listen for radio waves or anything that requires the distance to be considered. You can get the best revolution and the strongest signal strength and so on. And as the Earth rotates from left to right there, if you are only in a low inclination orbit, then you will actually go around all the time and look down only on low latitudes as opposed to a polar orbit, which is the way to get a chance to view all of the Earth. Thank goodness we have those, and we'll talk about a special case of those in a second. I'll try to move something off my screen for a second here. Maybe if I put it up here. Okay. The applications we know and hear about the most are probably in weather and weather forecasting and weather maps, as well as down-looking imaging and measuring in the earth science field. And thank goodness for now about 30 years, we've had constellations of Earth observations for all the spheres, the cryosphere, the hydrosphere, the atmosphere, the land masses, and so on. So now we actually can have a lot of confidence in understanding the way things work dynamically over long periods of time with a lot of revisits of measurements. And if we take a military application of the down-looking imagers, then we're talking about intelligence, or maybe we're talking about listening for signals. But they all happen best at low Earth altitudes. And then finally, we can do zero-G science most easily up there. And the laboratory, and you may know that the International Space Station is actually a national lab, one of the national labs. Been up there for over 2 decades now. And so it's the place of the most zero-G science, and manned activities have only once in the Apollo program left near Earth space. And now I'm trying to get my slide to change. There we go. A special case of a polar orbit is something that we can be very grateful for, we people that gather this data and need to analyze it over periods of time. Because when you go into certain solutions to the orbital mechanics equations, it turns out that if you aren't quite at a 90-degree inclination, the shape of the Earth, which is not a perfect sphere, the fact that it's flattened out toward the equator or oblate, and also somewhat pear-shaped, means that that perturbation of the gravity causes the orbit to walk, if you will, to rotate. So rather than being just this dark blue orbit which you can picture just staying there if the Earth were a perfect sphere, as the Earth in its seasons goes around and the sun angle changes constantly. With a sun synchronous orbit, you can calculate the combination of altitude and inclination to give you a rotational rate, which is around a degree a day, 360 degrees around, 365 days a year. And so for just slightly less than that 1 degree a day, you can have your orbital plane follow you as the Earth goes around the sun in the seasons and get the same sun angle and therefore shadows and things. So it helps you compare imagery and so on. All right, the next case that we're all familiar with of Earth orbits are those that, quote, hover, geostationary orbits. And there's a particular solution, which is that 24-hour orbit as the Earth rotates, as you can see here in the little pictorial. Looking on one of the poles, you see the Earth going around and the 24-hour period almost exactly of the satellite. If you put it at the equator, then it goes neither north nor south either, and so it appears to hover, which was predicted to be convenient, and you'll see in a minute just how popular and convenient it is. And that's a geostationary orbit. You may know that Arthur C. Clarke, the great science fiction writer of the last century, like H.G. Wells and who was it, Jules Verne, that inspired a couple of the rocket scientists. Well, Clarke was pretty clever himself, and I think it was back in the 30s when he came up with this in some of his writings and made it a popular idea long before Sputnik went up. So we understood what it would be, and today we get to take advantage of it. If you don't have a zero inclination orbit, the more general case, then you basically have figure eights that move above and below the equator with their footprint on the ground. The common applications, I've mentioned comms, those are the main ones. Also meteorology in quite a different and complementary sense than the low Earth orbiting weather satellites. We now have a number of geo-orbiting macro scale weather observations where you see the entire hemisphere. You get to see the interaction of weather systems crossing the oceans very nicely and so on. And so when you watch the news, you get to see some from all these kinds of satellites. So just a really important kind of view of how popular and valuable GEO is for communications, whether it's to actually broadcast or whether it's to relay signals that come up from the ground or from satellites in low Earth orbits that can't see their ground stations and use the relay to go up to the GEO and then back down to the ground station, basically jump the radio signal around. The applications are very numerous. The communication systems, the cell systems and so on are very numerous. And there are literally over 100 communication satellites out there in operation right now. This is a tilted figure. It's not an ellipse, it's a circle. And it indicates at each of the longitudes going around what the population out there is for different numbers of satellites, with the color coding, if you can read it, to be the frequency bands. One last thing I'll say about GEO is that there has been a technique to get from liftoff to insertion at the 22,000 plus altitude that's been used for most of the launches. It was invented by, I guess, a mathematician in the 50s, I believe, Hohmann. It's called the Hohmann transfer ellipse, and it simply works this way. You use your booster and often a second stage to get up into a fairly low altitude LEO orbit, and you would just go around in that circular orbit if you didn't do something, but you pick your place based on the longitude that is where you want your geosat to appear to hover, And 180 out from that, you have the first burn of your engine. And that puts you into that red orbit that you see there, leaving Leo and headed on an ellipse now towards the correct altitude for GEO. And once you get there, if you didn't do anything, it would just come back in on the ellipse and to its perigee where the first burn was. But once you get there, you circularize the GEO orbit with a second burn. It's all done with something that is pretty obviously referred to as an apogee kick motor on board. So that's a common technique to get to GEO. And in between these highly populated areas, much more highly populated low than high, is that vast range from 1,200 miles up, which is used from time to time because it's got advantages like if you have some kind of a relay spacecraft that you don't want to have as much signal strength from the ground, then you'd rather be closer down. And on the other hand, you don't want to come all the way down to a low Earth altitude because the coverage footprint is so small before it goes over the horizon. And so kind of in between are these compromise solutions. Better signal strength or less power required to get a signal if you're in the medium compared to GEO, and a better resolution, a better footprint field of view for imaging, but worse resolution as you go up. So there are trade-offs, and once in a while, there's something that wants to take advantage of this, which we tend to refer to as a Goldilocks application, not too high, not too low. And so cellular telecommunications has turned out to be the most popular thing for that. I'm not sure. I don't think Starlink is a MEO. I think it's Leo constellation, but I'm not sure. But there have been a number, like the original Sirius and XM used spacecraft that were in MEO orbits. You needed multiples because it went over the horizon sometimes. Here's a picture of the most popular application, perhaps of anything for the average citizen, and that's GPS. So navigation satellites, if they're put up into a number of planes, can allow the signal to be seen from any one of literally dozens of spacecraft at any point on Earth a number of times before that satellite goes over the horizon and the next one has come over another horizon. So the little model there's got a counter that shows for the period where all those green arrows point to, for the place on Earth where the green arrows are pointing, that's where that spot is seeing that number of satellites all the time. You want to have a lot more than just a few to have precision. And 7 to 11, which is kind of what goes on here, is very adequate for the very high precision that we all enjoy with our GPSs. And there are, incidentally, also there's GLONASS, a Russian system. There's a Chinese navigation satellite system, and there's one other. It may be Japanese. I'm not sure. All right. So that's enough on orbits. Let's talk about what we want to get up there to use for our mission. And so what we have then is our spacecraft on top of our booster and upper stage sometimes. And it has a very simple mission. It carries the payload. It cares for the payload. The payload needs to have power. It needs to have certain things. Now, having said that, there are, and it's known as the mothership for the payloads. And so you're going to see that in some cases, it actually stays with it. In some cases, it deploys. And so, for example, if you consider a person, an astronaut going to the space station to be the payload, that's where you get your payoff. You put a man up there or a woman up there, and you get to have them operate. They have to be carried by a spacecraft, for example, Crew Dragon. And once the spacecraft has taken care of them and carried them, then it deposits them there and fortunately can come back and take some more some other time. But at any rate, it's all autonomous from the payload itself. The person is autonomous from the spacecraft. Probably in most cases, the payload, whether it's instruments or measuring devices or listening devices or whatever, stay with the spacecraft and aren't just carried and cared for on the way up, but throughout its mission. Some examples of payloads, there are just almost an endless number that have been used and put up into space in the last 60 years now. All kinds of instruments and communications devices, and sometimes magnetic measuring and gravitational measuring and so on. Sometimes payloads that are carried somewhere like the atmosphere of another planet or moon, like Huygens, sometimes carried to another planet and land on the surface and drive around and so on. Those are all sort of the end product, if you will, that gets the actual value that the mission needs back to Earth or back to the spacecraft carrying it, and the spacecraft gets it back. So categories of spacecraft, flybys are quite different than orbiters. The original approach to visiting other heavenly bodies, first the moon and then Mars and Venus, was always a flyby because it was much easier to get close than to get on the surface or into orbit. And so we had a number of them in the 60s. And then we got on to the grand tours, and a flyby like Voyager 1 or Voyager 2 is easy to understand what this means, because they go to one of the outer gas giants. And in one case, it went past Jupiter to Saturn and then on to Uranus and Neptune, and so went past 4. And each time the trajectory was planned in such a way that it flew by at a close approach so we could get good imaging and perhaps some measurements. And so the compromise there, of course, is all you get to look at is what you effectively swoop down and go past at a very high rate of speed. And you don't get a chance to see the other side or anything even out of the vicinity of the closest approach. And so that's the flyby approach. Then we got to where we could actually insert ourselves into orbits, and Cassini's a prime example of that around another heavenly body. We have a whole set of observatories in space. Question? I hear a question. Anyway, if you do want to interrupt, please, Jeremy, I'll leave it up to you if you want to interrupt me. And I'm happy to take questions. So the observatories are quite a few that have been there. Some have been up. Some have been up and are dead now.
Really good defense. I think the key is going to be Kanjani Juzang.
At any rate, observatories, third category. Communication satellites we've talked about. Sometimes we actually go into and through the atmosphere, like we did with Venus initially, like we did here with Huygens 15 years ago at Saturn, or I should say at Titan, the moon Titan. Sometimes we actually go down to the surface, and here's the most famous early one, with delivering its payload of people there onto the surface. And sometimes we deliver landers and sometimes even rovers to drive around and effectively be science labs. As a matter of fact, the name of Curiosity formally is the Mars Science mission. The final one I'll mention, special category used for comets like this or for asteroids. You get close, sometimes you go into orbit, and sometimes you actually have a device that goes down to the surface, kicks up some dust, which you image with another spacecraft, or a couple of times now, kicks up some material, captures it, and physically it brings it back to Earth. So we've got all manner of types of spacecraft missions. And we have a whole range of sizes and complexities moving from left to right. The smallest and simplest, of course, was this one. Very small, didn't do anything but beep, but it revolutionized mankind's exploration. And you might think that the second one, but it wasn't the second, because before we could get up there, the Russians had launched a second Sputnik. So the third one that got up there was also pretty simple, but it did have a scientific purpose. The Explorer, the US held here, very small upper stage and space and payload, with von Braun and Pickering from JPL and Van Allen holding it. Then we move way up in size to one of the largest, the Hubble Space Telescope, like a school bus, quite a complex vehicle, extraordinarily valuable machine for science especially. And coming soon, I can finally say, will be the next great, very large, complex telescope, which in the case of complexity here, much more complex in terms of constructing itself literally on orbit in order to be a very much larger primary, and also a very much more highly focused primary, which is even now is underway, and hopefully we'll be seeing those first images within 2 or 3 months. The Webb. But we're going to talk about another old favorite spacecraft to talk about what's actually the functionality and how it's done. We'll talk about this one, the good old Cassini, which we had a talk on to your club, I think, several years ago. Here's, you may remember, an image of the test chamber holding Cassini and Huygens, the Titan lander there in the foreground. And it's a nice snapshot to illustrate just how huge this spacecraft was. The most successful spacecraft ever, large spacecraft, or I should say the largest size successful spacecraft ever. You might also argue that it was the most successful. At any rate, you see the statistics there on it. Weighed 6 tons, over 2 stories tall, and so on. And because it was so big, we had to use gravity assist to get out to Saturn, and so it took a very long time. Saturn being roughly 1 billion miles away, but we went around planets 3 times and around the sun in order to get up enough energy to get out there. And after insertion, do almost 300 orbits around Saturn, almost all of them different than the one before, on the order of weeks to months for the orbital periods, in order to have the execution of planned trajectories that took it very close flybys of many of Saturn's moons. A very exciting science take indicated there at the bottom. And lots of research, I'm sure, yet to be done with the Cassini data since the mission only ended a few years ago. All right, so we're going to look at the subsystems to understand how every spacecraft works. Every spacecraft has to have these subsystems on board to support the operation getting to and then operating in place if it does support the payload there. The first one I'll mention and only say these few words about it. The others I'll talk about with a single slide, but from the beginning, some kind of a brain was usually needed on board the spacecraft. Not very sophisticated. Remember, this was initially it was 40s to 50s technology, and then finally 60s. There wasn't anything solid state about some of the earliest ones. There was nothing that was digital computers for quite a while. And yet eventually we got to having very sophisticated onboard computer capability. Even at that, Cassini is a good example of how it does tend to lag where we are if you have a long-term mission. Cassini was designed in the early 90s using digital computer technology from then, meaning only half a meg of RAM in these flight computers and only a total of 2.3 gig on board. And you know, if any of us looks at the specs for the laptop that we're looking at, of course, it'll be much, much greater than that. But it was enough to gather that enormous amount of data. And when we talk about the communication system, we'll understand why. And there are other kinds of computers on board to do star matching for orientation and things such as that. These are the other 6 subsystems we'll talk about. And one final point before I just kind of dive into these. The principle of redundancy is really, really important. The cost of these ranges from hundreds of millions on up to a number of $1 billion. And 99% of them are going to be put into a position to perform their mission, usually a LEO, but in a way that they can never be visited again if something critical breaks and you want to repair it. And so it became a principle early on to do failure mode analysis and figure out the single point failures and try to have, for the major systems that might cause mission failure, redundancies. An example I mentioned here we'll look at in a little more detail when we get to the propulsion system, but really critical to think through and calculate those things that 5 years into your mission, if you don't have it anymore, it just stops your mission dead. And unlike Hubble, which we visited 7 times, almost no other spacecraft have been visited like that or have the capability even. So the first subsystem I'll talk about, probably the simplest, with just a quick look at Cassini hanging there on a rig in a chamber of some sort. You can see most of the mechanical subsystem. Every spacecraft holding a payload has got some kind of custom designed structure to hold things in the right balance with the right, if you will, shock isolation and so on. Lots of calculations go into these designs, even though they are just cold mechanical things. And so you have to look at the statics as well as the dynamics, and you come up with your spacecraft bus design, everything mounted to it. The fact that spacecraft have their own custom diameter usually at the aft end, and boosters have a variety of diameters on top, you have to match that. And so often you build a custom sized launch adapter ring. And then not obvious as being something other than the spacecraft perhaps, but it is, and that's this ring that's mounted and holding the high gain antenna to hold the whole structure in place. I'm sure it was quite an expensive item to design and build, this particular lifting handling ring, and it's part of what we used to call the aerospace ground equipment, AGE, or GSE, the ground support equipment. So there's quite a bit of mechanical subsystem for each spacecraft that is custom but doesn't fly with the spacecraft. Next subsystem here in the upper left is a favorite picture of mine at the launch pad. We used to look forward to the day when you'd see the technicians out there putting these reflective thermal blankets on the outside of the spacecraft, because it meant that we were done with all the months of preparation and integration. And once you put these on, you can't get at what's behind them. And so it meant that it was about to be put into the fairing and launch would come pretty shortly. At any rate, it's the passive way of handling temperature ranges, and there are extraordinary temperature ranges. From one side to the other, a range of about 800 degrees Fahrenheit from the side looking into the cold of space versus the side looking back toward the sun. And so it's really important to try to dampen that out thermally and protect the innards, and use other devices like heaters, radiators when you have an active device, thermally active device inside that needs to have some of the heat dumped through louvers. Sometimes when you turn around on the backside after heating up something, you close the louvers to hold the heat in. So there are a number of active components to the thermal system always. And I should say, we can't go into it. I don't have the details for one reason, is James Webb has an extraordinary challenge now, as hopefully it has its decades-long mission to always keep the sunshade toward the sun and never ever allow any of the instruments and the primary and the telescope to catch a glimpse of the sun. And so when you talk about safe modes and sun sensors and things like that, I'm sure they've got plenty of that on board for it. Next subsystem is one that is where Cassini has a configuration that at first glance doesn't look like many of the near Earth satellites, because there are no wings, there's no solar panels, none at all, and in fact no batteries, because 10 times out the distance to 1 billion miles versus where Earth is, that's the distance of 10 squared, or 100 times lowering of the signal strength. So the sun's strength. And so it's like 1% of the sun's radiation is received out there, and therefore you need to do something else to get your power. Solar panels won't do it for you. And what they did, and here is a picture in the upper left of a close-up of one of these RTGs, was use these things that are colloquially called nuclear batteries. And so with radioactive isotopes, in the case of Cassini, with 3 of them mounted around the aft end here of the spacecraft bus, you take the heat of the decay and you use that with thermocouples to generate electricity on just a steady basis. And so you get DC power that lasts for decades if you have radioactive isotopes with a long half-life, as the selected material, plutonium-238, is. What that means also is that over a long period of time, the radioactive substance has decayed and therefore isn't there, and whatever number of pounds you had, in this case 73 initially, has decayed somewhat, and you have less power, and you have to manage that. It's notable that we don't launch RTGs unless we need to, because we're very careful about putting any radioactive material in the atmosphere. And regardless of what the launch risk is, especially near land, probably the worst case is at some altitude. What you do not want to do is have a catastrophic explosion spreading 73 pounds of plutonium forever, roughly, as it disperses through our atmosphere, and have the increase in hazard from that. And so you have to do the calculations, you have to get permission. For a while, they had calculated that the risk was, I don't know, 1 in 5,000 people would die of cancer. I'm sorry, I think that's what it was. It was quite a high number when you considered it on a global basis in a catastrophic failure. And then I think they discovered they'd done the calculation and screwed up the decimal point by 2. And so it was not 5,000, it was 500,000. So it was safe enough to launch. These lasted through the mission. They provided, believe it or not, less than a kilowatt through the mission, down to only about 600 watts at the end of the mission, a lot less than a hairdryer. And imagine with all these instruments and all the communications, managing to have everything run with just that amount of energy. So the electricity budget really took a lot of planning and calculations. All right, the next one is the propulsion subsystem. And we'll talk first about the most powerful part of it, which is those rocket motors down at the base. They were much tested by the time they were used on Cassini. And there are two identical R4D engines. They were fired a lot, as you see from the little note there, 183 firings. Most of those were once they got to Saturn and went into orbit in after 7 years, they had to change the orbit fairly frequently in order to have those 300 orbits that I talked about. And the main engine was used for that. The other propulsion aspect is these gas jets, thrusters, on the end of each of these four legs, with two opposing in the primary set and two in the backup set. So 4 on each of the 4 legs, 16 total, 8 of which are the primaries and 8 of which are the backups. And the use of them allows you to, by firing different ones in pairs, to roll or pitch or yaw the vehicle as you wish. And as it says, they were used for trajectory course correction on the way out, and they were used a lot for controlling the attitude of this vehicle, which you'll understand better in a minute when we talk about how they got their data, how they captured their data. The dominating feature of this picture, which has the outer part of the spacecraft bus stripped away, is this thing that looks like a medicine capsule, a huge capsule in the middle, longitudinal, and at the top is one of the 2 bipropellant tanks, the fuel tank, which has multimethyl hydrazine, and at the bottom, hidden, is an identical tank with the hemisphere at the bottom there. You can see that's the oxidizer, the nitrogen tetroxide, and basically that was the lifetime determinant. It was used to fire the main engine when you needed to. You changed orbits a lot. You had to use it sometimes to actually move the entire spacecraft to point things. And so once you ran out of gas, basically, you couldn't do anything else with your mission. So they kept track of that. And they had more than half the mass of the vehicle loaded with it at the beginning, and almost none of it at the end. The other tank that you see, the green arrow there, the sphere on the side, is not a bipropellant, but a monopropellant, because the hydrazine goes through a catalyst bed in order to generate the gas, which is used by those thrusters on the legs. And finally, every spacecraft has one of these, usually a spherical helium tank, which is charged up at liftoff and is used throughout the mission in order to provide topping pressure, if you will, for the propellants as they're drained out. You have to keep pressure on top of the propellant inside those tanks. So it's another aspect of the plumbing that makes the whole propulsion system work. So as I was saying, the mission duration was determined by running out of gas, and more than 99% of that, more than 3 tons of propellants was used up over 13 years of operation on orbit. The next subsystem, TT&C it's called, just think of it as the communications subsystem. The dominant feature here is that big white antenna, which the Italians, it was their part of the program actually, and that high gain antenna was really critically important because the computer resources and in particular storage on board wouldn't have allowed you to have much data on board for very long. And so you had to downlink that data periodically. And so the asterisk note there says, and it's not that they did it exactly every day, but on average, they downlinked data for about 9 hours a day and uplinked commands as needed or software uploads. So a lot of the activity on orbit at Saturn was turning back towards Earth and using the high gain antenna for communications. And not only did they have that antenna, they had a number of components that we won't go into, such as signal conditioners for the instruments, do some, pre-processing of the data before they would communicate the packages back to Earth, receivers, transponders, and so on. All right, and so finally, we've got this two-story observatory. And I just want you to understand that every instrument on there, and there are over a dozen of them, is in fact hard mounted to the bus and is not articulated. So you can't point anything. You can't point your imagers. You have to move the entire stabilized observatory in order to take the data in whatever spectral band as you do a pass past a particular moon, for example. So you can picture this dance now that this very large, very massive spacecraft is doing as it pitches and rolls in order to point each of the instruments at the right time per the schedule in order to capture the data. I think the operation of this must have really been fun and a continuously challenging activity as you changed orbits and picked different moons to try to look at different parts of, for example, through the mission. One of the things I do want to point out, though, is that it's used for moving the spacecraft around was necessary to point the instruments. It was also really important for it to point that large antenna. And so I'll just highlight the sun sensor there. Looking through that antenna dish, bore-sighted with it, is a sun sensor, and you might ask why, especially there. And the answer is because Earth, when you're 10 AU out at Saturn, Earth at 1 AU is effectively in the direction of the sun all the time. And so the crude pointing of this entire observatory was done simply by looking for the sun and slewing around and pointing at the sun. And then you were effectively pointing with a signal that could be picked up by Earth and its deep space network antennas, these antennas, some of which are 70 meters. And that was done, as I said on a previous slide, for hours a day on average. So you'd stare back, you'd send your data down, you'd get things uplinked. And that was one of the things that you did with your navigation and control systems with this particular sensor to point you. And then you had the fact that the precision pointing of all these instruments required other kinds of pointing capabilities. One of them near and dear to our heart is simply those two telescopes effectively on the side that you see cross-hatched in blue there. They're identical. It's a redundant set. And they track this, they see stars, they compare them to the onboard star map that they have, and they give you your reference. Also the typical kinds of gyroscopes and accelerometers for stability and for sensing any sudden movements or anything like that. The pointing and steering, as I said before, was done at the first order by using the gimbaled main engine. And this was particularly important when they flew by this very large moon, Titan, because Titan, as you probably remember, is shrouded, very thick atmosphere, and therefore you need to look through it with an appropriate frequency, microwave and active microwave if you want to get any imagery. And so the active sensing, also known as radar, would create synthetic aperture radar images by slewing that high gain antenna. The same antenna used for radio communications was part of your synthetic aperture radar system. And so when you had a typical pass of Titan, you can picture, you'd pick the ground swath that you wanted to paint at whatever altitude, and then it would have to rotate, get positioned, and get ready to take data as you went past the low point of your flyby, and then point back at that area in order to get the longest swath. And in order to do this, you needed something more than just thrusters to point, and so they used the main engine in order to point the entire vehicle like that for these particular passes. And there were over 100 passes of Titan through the 13 years. The thruster clusters were also used during the Titan flybys in order to rotate the vehicle for the variety of instruments, especially the VIMS was used at Titan, and any of the moons, these different instruments would be used. And so you see there that set of of 8, 2 per leg were used for that. It turned out in, I think, 2009 that the primary set was acting up, and they brought in the backup set, and so they got an additional 8 years. The last 8 years of being able to point was because they had redundant thrusters on board. And finally, for pointing, you may be familiar with these reaction wheels. There are different names for them: momentum wheels, reaction wheels, something slightly different called control moment gyros. But they all take advantage of the fact that if you have a large, perfectly round, or I should say perfectly disc-like rotating wheel, then you generate a lot of angular momentum. And as you're probably aware, like when you push on a spinning gyroscope, it resists, and actually it exerts a torque that's at right angles to the way you push. You take advantage of that, and you actually steer this entire massive vehicle with 3 reaction wheels. A lot of the steering was done simply with those. There were 4 on board. One of them didn't last, and so they had to pull in the backup. You see reaction wheel 4 there. And so those 3 reaction wheels were used throughout. There's a picture of one of them. And by changing the rotation speed, which typically is in the hundreds to 1,000 or 2,000 RPM, you change the force of the angular momentum on the body of the whole mass of the vehicle. And at different angles, therefore, you can actually roll and pitch and yaw with these 3 vehicles, which they did. Very fine pointing capability. They ran all the time. You see the pointing accuracy that you got there, and you see the last bullet, which is that they've never had a set of wheels that has been this reliable and lasted this long, and I say thank goodness. So that's kind of it for the subsystems of any spacecraft. That's the example from Cassini. They all have to handle navigation and communications and propulsion and thermal control and the mechanical structure somehow, and that's a pretty complex one. In the future, we are challenged to find a way to not have to spend quite so much money gathering all this science, or to accept the fact that you only get to visit something once in a while for a long period of time, and your technology after a decade or two you wish might be better, but it won't be, because you can't afford to go back up there very often. So instead, we're being driven all the time by cost-saving pressures. And the answer to that, in a generic sense, is to make things modular, to make them repeatable. And that's been the wave of change in spacecraft now for whether we realized it or not, for about 20 years. It's really quite remarkable how many of these various small satellites now have not just been designed, but have been used, some of them for actual operations, not just for research. And I draw your attention to the website, nanosats.eu at the bottom there. A European group does us the favor of keeping a really extraordinary database online. They keep it up to date of who and how many and what kind and so on small satellites there are. There's a whole set of defined categories once you get under about 1,000 pounds for your payload. The ones that you hear about the most now are in the nanosatellite category. That's where the CubeSats fit. CubeSat isn't a generic category. It's just one of the ones that, for obvious reasons, has shown up in that particular band of weights there, up to 10 kilograms, about 22 pounds. And when I say they're proliferating, and this is from that nanosat database, there have been almost 2,000 of them launched now. They've been launched by many, many more nations than could have launched things if the budget for doing these weren't quite small. The US, as you see, dominates. 2/3 of them are US launches. China and Japan are in there, but 2 orders of magnitude almost less than we have done. And then you can see across South America and parts of Africa that nations that never imagined, 25 years ago, that they'd be launching satellites are now launching some of these nanosats. roughly 90% of the total launched are CubeSats, which we'll look at here in a second. And there are lots and lots of companies that are coming and going in this space because it's a very attractive one for companies that can start up and deliver things at affordable prices, which is the whole key to the thing, affordability. So here we have in the table there examples of 3 CubeSats, the 3 that are closest to us. In the background is something called a P-pod, which is a standard structure to hold 3 of these and probably eject them at the appropriate time, or maybe so that they can be used in conjunction with each other. I don't know. But basically what we have then is this kind of Kleenex box sized satellite. It's called the 1U standard. And it typically weighs just a few pounds. And we have these in a variety of configurations. Engineers among you will, be used to using the term form factor and standardization. And that's what we've got here in this particular part of the industry. And you can rearrange these modular items in whatever configuration, but there are some common ones that you can picture, like the 6U compared to the 3U that would fit inside of that P-pod there. And the 12U would double that. And there are different geometries you can use to put them together. So it's a modular standardized approach that's, as I said, 90% of them have been these, extremely popular. And along with everything else for affordability, since we've got so many miniaturized to the nth degree, chips for computing and processing and communications, pre-processing, and all kinds of off-the-shelf COTS, commercial off-the-shelf functionality today. And so these folks that are designing and trying to corner a part of the market are looking at ways to take this off-the-shelf set of technologies, package them so that they're modular and can be easily configured. And the launch vehicles will be glad for that too, because they don't have to do so much modification, so much customization. And as you might imagine, it's the folks that couldn't afford before that are now affording these things. The government and the military in the big nations still have their big budgets, but most of the universities and many companies that wanted to try to either test a commercial proof of concept or do some research are now able to do that. And so that's who's showing up. And so there are all these applications. Here are a couple examples at the side. You can picture at the top there. It looks like it's solar cells on the outside. So that could be the power module of a set of CubeSats that work together for your spacecraft. You have perhaps an additive manufacturing based structure there to hold whatever it is you want to put in it on the right side. And you've got literally hundreds of these configurations or these candidate offerings being pushed forward now by industry, especially given that with the smaller size, with the need to, if possible, for affordability, use the lowest possible orbits. You're going to want to have constellations of things because you're going to go over the horizon from most places pretty quickly if you have something that needs to communicate. So it's, for me, I was Lockheed's director of e-commerce initially back in the 90s. And so I witnessed what we used to call the Wild West there before the internet bubble burst. And today's small sat market feels a lot like that. It'll be quite a long time before it gets shaken out. Hopefully they won't have the small sat bubble burst like we did in 2001 for the internet. But at any rate, at some point, maybe 10 years from now, there won't be hundreds of these anymore. There'll only be dozens of them, and we'll actually know the names of some of these companies. So that's the state of spacecraft today and tomorrow. And that's it, looks like. Thanks for your attention, and I'm open to any questions.
Great. Thanks, John. That was great. Actually, I have two questions from YouTube. Question number one is, what are the benefits of a Lissajous orbit around the Lagrangian point? So I think that's relevant to the James Webb. And the second question is, how can low Earth orbiting satellites be better designed to avoid impacting astronomy? I guess that relates to Starlink and things like that.
Let's take them one at a time. I'm a little slow. Okay, Lissajous orbits. Lissajous used to be challenging with an oscilloscope, if I remember, about 50 years ago in grad school or something. But at any rate, I hardly understand the question, and I'm not very sharp. I will tell you what I do know about the halo orbit of the James Webb, which I think you may know this, but I'll just tell you because it's kind of interesting. The reason that it didn't just go out to the L2 Lagrange point and station keep there effectively is because by definition, the Lagrange points are in the line of the two bodies, the sun and the earth in this case. And so it would always be in the Earth's shadow, which might sound like a pretty good idea since what you want is cold focal planes and so on, except that if it ever drifts out, the expansion contraction problems they would have to deal with if it drifted into the sunlight once in a while was something they decided from the outset they couldn't stand. And so they designed it with an orbit that keeps it always out of the line. It keeps it always in the sun, if you will, in an orbit that is stable in the sense that you can orbit around a Lagrange point, and that's what it does. As far as what that means with the term Lissajous, I don't know the answer. Does anybody?
I guess the idea is it's a 6-month oscillation around L2, and it's a 12-month orbital period of the Earth. So I guess that's where the Lissajous comes from.
I see. Okay, so it's always a multiple like that, a harmonic 6.
Yeah, when you were playing with the oscilloscope, it was when you had like frequency on the X and frequency on the Y, harmonically related.
Right. Yeah. Yeah. Playing is what I did. It's a good term for it.
Yeah.
Double E wasn't my thing. The other question?
That was about low Earth orbiting satellites impacting astronomy and what could be done to try to minimize those impacts.
Oh boy. That's not a question I can answer so much as come around to your side of the table and perhaps complain along with you. I've been really upset about this since it became evident what was going on. You're probably aware of the little bit I know, which is that they, what's his name, Musk and company decided to tamp down some of the some of the noise first by designing, I guess it's kind of like an awning on these things that keep the most reflective parts of the blocked from the ground, which of course doesn't mean that it's not there and blocking you if you happen to be trying to view an occlusion or something like that, but it does keep it from, being a light in your telescope. It's amazing to me how governments work, but the governments now are finally getting together and meeting to decide what, if anything, can and should be done about this. Talk about the horse being out of the corral. I think the number of satellites in Musk's Starlink constellation is over 10,000. And there are 3 or 4 other named constellations that have been planned and are starting. It's a ridiculous number, and it is. I saw calculations recently whether it was in the Reflector or one of the magazines that probably a lot of us look at. There was a good article about it. It may have been in Reflector last month, but I'm not an expert in it. I'm just a person that's really disappointed that we've gone this far without knowing that it was going to be a problem.
One more question from YouTube. Beyond what approximate distance do we have to start using deep space network to communicate with satellites versus the simpler means?
I'm not sure. Maybe I have had a couple of good lectures on DSN. Maybe I'll give a talk on that soon. I'm looking for topics to do next, and maybe I'll think about that. It's quite an extraordinary, and you may very well know, very long in the tooth. I mean, it was developed for Apollo initially. So it's been around for 50 years, and it's been around at 3 locations so that as things out there don't move much and the Earth rotates around, you can always see one of the locations in Australia, in Goldstone, and I'm trying to remember, Scotland, is it? I'm not sure. The third one, or maybe it's Spain, the other one. At any rate, multiple very large antenna, and the answer to the question is probably that there are some low Earth orbiting spacecraft that use it, but I have to go back and look at what the guy talked to us about to give you a better answer to that question. Yes, it is very definitely used for deep space launches.
So certainly interplanetary.
Yes, and lunar too. Yeah.
Lunar
Yep.
missions use it as well.
Yeah. I mean, Cassini's an easy thing to see because the signal strength is bound to be pretty low. So you need giant antennas, like the 70 meter is what they have. And, since it goes as the square of the distance, once you get very far out of low, Earth orbits, you need a big antenna in a hurry.
Other questions?
Question?
Yeah, Nelson?
Yeah, hi. Hey, thanks. John, 2 questions from 101.
Yeah.
Orbit insertion. With the graphic you showed with the mountaintop and shooting it off, is it possible for a change in the vector of the delta V to have no second burn at the apogee to round the orbit? Is that possible?
Typically, you're probably aware of this. Once you shut down the engine, you coast, i.e., hopefully you're orbiting all the time until you have another thrust, another delta V, as you said. And so if you have a perigee on one circle, the low Earth orbiter, or a medium Earth orbiter or whatever.
Launch point.
Yeah, that is by definition, if you don't do anything other than burn there, going to be your nearest approach on an ellipse. You put yourself into an ellipse. You don't put yourself into a circular orbit. You can reach the altitude where you want to have a circular orbit, and then you have to apply the delta V in the appropriate way in order to circularize at that point, okay? But without a second burn, you don't go into another circle, you just stay in your ellipse and just keep going in orbit around an ellipse.
So there's no way of changing the component of the delta V in the orbital insertion to fix the perigee from being your launch point to someplace out of the atmosphere.
The perigee is going to be the perigee of your orbit until you change it by injecting energy somewhere in the orbit. And so obviously for GEO, you want to inject that energy to circularize at the right altitude.
Second question, also 101, is POGO solved? The POGO oscillation?
That's a good question. You that shows some some experience. May I ask you the quick question? From what do you remember this? From maybe what decade or what time?
Oh, from S1B.
Okay, yeah. And Titan in particular suffered from POGO. POGO is, to everybody else, kind of what it sounds like with regard to a thrusting rocket engine. It's when you start having accelerations and decelerations along your longitudinal axis that you don't want. Obviously, it's like a compression rarefaction, if you will, as you move forward. And obviously, you don't want that if you can avoid it. Like a car with a couple missing distributor wires or something like that. By chance, just a quick anecdote. I knew a little about it, but then I worked for a guy who had been with Martin Marietta, who became my boss when GE and Martin merged in the 90s. And it turned out he was one of only 2 or 3 experts in the world on POGO from the Titan launches in the 60s and 70s. So he told me, no, it was pretty well solved. Yes, to answer your question. Yeah.
One more question, if you would. You're more acquainted with the Saturn probe. There were 183 restarts of the main engine, for a 100-pound engine. What did they do for ullage? The
ullage, well, that's what the helium tank was for, was to pressurize the top of the tank.
Was it a bladder?
I don't believe so, no.
Oh.
I don't believe so. Now,
okay,
let's see, the key word in that sentence was believe. I should have said think. I don't know.
yeah, it's, all right, well, thanks.
Yeah, maybe there was an inner bladder that was compressed increasingly by helium between that and the skin. I don't know.
I appreciate your presentation.
Okay.
Thank you so much.
Mm-hmm. Anybody else?
John, as I remember it, the RTGs for Apollo were made or designed in King of Prussia by GE. And I was wondering, are they still in that business?
I think you're right. I joined up in '77, and it wasn't anywhere near the part of that very big organization that I was in. But I think you're right. I think they were built by GE. And of course, GE got out of the aerospace business when Jack Welch sold us in '93. I shouldn't say sold us, sold them. And of course, GE today is a completely different company than it was back then in most ways. But I don't know who does them today.
Thank you.
Mm-hmm. Feel like I'm talking to George Washington there. Is that correct?
No, that's a great, 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 great grandfather.
No kidding. Yeah. Well, very dignified.
Other questions?
Yeah, John, all these constellations of satellites, do they present a danger of the Kessler syndrome?
Is that the cascading?
Right.
Yeah, I'm sure they do. Yeah, I think if I remember, I think that got mentioned in the article that I was looking at. Yep. Yeah, I wish I did understand it better. On the other hand, it worries me, and especially since, like climate change, we aren't taking it seriously and doing anything about it yet.
You would think that one small asteroid going through that mess could create quite a damage.
Mm-hmm. Tried to do my own calculation recently, just to, kind of represent the volume in that tube of low Earth orbiting altitudes and calculate, with the denominator being the number of objects, and see the average distance between them and so on. And I don't think I did it right, but it wasn't a small distance. I mean, that's a huge volume that these are orbiting in. Having said that, there have been collisions, and there have been plenty of times, I think, in the space station where they've had their alarm go off that they get ready because something might be passing near and they just want to be ready for it.
John, quick question for you.
Mhm.
Are Molniya and Tundra orbits still used, or have they kind of fallen by the wayside?
Give me just a second here. Let me look at a slide. I was going to talk about them. I didn't know if it would be of interest, but let me see if I can look at that slide for a second. I'll be right back.
Sure.
You're not sharing my screen, are you?
No, your screen sharing is off.
Yeah, give me just a second here. I know where I put it.
I always thought those are kind of interesting orbits because you can do a lot of unique stuff with them.
Very. So let me just read you. I've got some notes here on it. A tundra orbit it's geosynchronous. It is not circular, okay? And so why would you do that? Well, if you could have one where your perigee was, say, at exactly the latitude that you wanted your spacecraft to spend most of its time within view of, say you wanted it to be within view of 50 degrees latitude, you would then pick 50 degrees south latitude, and you would put the perigee of an elliptical orbit, because according to Kepler's third law, you dwell basically in the long part of the ellipse. So you'd be up quite high, but you would still be having a period of one day. And so every day for most of the hours of that day, you'd be viewable from a very northern latitude, as opposed to, it wouldn't be geosynchronous, but it's a lot closer to having continuous coverage than if it were a circular orbit or some other orbit. So that's a tundra orbit. Molniya, I remember these because, as you might guess, the Russians discovered this orbit and used it first. Let's see, I'm just reading my notes here. I knew about them back in the 80s, but I've forgotten a lot of it. Let's see. It's one of these middle altitude orbits that has a period of 12 hours. So each of the satellites in a 3-satellite constellation, circular constellation, like the GPS satellites are, they're 12 hours. But in the case of Molniya, For communications, they use this because if you put equally spaced 3 satellites 120 degrees apart, then you get constant coverage from one of them and you get an overlap of 2 of them for a while before you lose one. So it's a very convenient kind of a communications relay capability. And like the other, you can design it for whatever latitude you want it to be over. So that's the quick stuff I remember about them. Your question was, are they still using them? And my answer is, I don't know, but I wouldn't be surprised. And that's about it.
All right, thanks. We do have another question from YouTube. This is, does the tiny atmospheric drag experienced in low Earth orbit limit the useful lifetimes of CubeSats and Starlink and things like that?
Well, you know, drag's always proportional to the cross section of the vehicle. So to the extent that CubeSats and nanosats are small, it won't, that'll be one part of the equation that will be forgiving, but drag is drag. And so say at 100 degrees, 100 miles up, I should say, a large satellite will decay fairly rapidly from there. And I imagine the CubeSats would be able to stay up much longer. I'm not sure that, you know, they might have really, you know, any kind of useful lifetime you want without really worrying about it for the low altitude, for the small cross section they have.
Thanks. Other questions?
I have a quick one. On the manned spacecraft side, you've got, you know, 3 different entities now, either producing or developing manned capsules. And, you know, you've got United Launch Alliance and SpaceX and Space Launch System developing or having heavy boosters. And that doesn't even bring in like Blue Origin or anything like that. Do you think all this redundancy is good to have, or do you think it's a waste of money?
I think it's inevitable, I guess. And it's interesting, contrast our capitalist system, which has all kinds of people who, you know, don't even have to be that wealthy to start up their own companies. There are dozens of launch companies around the world now that see the opportunity, whether it's by using an aircraft as the first stage before they launch their rocket at some altitude, or they have developed their own booster, like trying to remember the names of some of these companies. They're in the news a lot now. There's some very successful ones so far.
Like Astro is one of them.
Astro is one of them. There's another
Rocket
one.
Lab.
There you go. That's the one that's both in New Zealand and I think up in Alaska. Yeah, these guys are likely to have at least 1 or 2 of them that end up being the winners over the next 5-10 years, I imagine, to get a lot of the small satellite business. And then there are some larger ones, or some that are looking to get heavier masses into low Earth orbit that are going to take longer to come along. And of course, Blue Origin you tossed in there, and of course it has been successful with the New Shepard. And if they ever get the New Glenn flying, it will have much more massive launch capability, not like either the what do they call it, the Starship, or the SLS even, but I think bigger than anything else. And ULA, I'm not sure ULA will survive. I mean, to me, they look like the story of what happened to many companies with the startup in the 90s or so of technologies. Here's an example. Southwest Airlines came along, and because they were new and could afford to take the latest generation technologies for their infrastructure, they were able to drive costs way down. They were a real intrusive company. Obviously, they succeeded at it. Companies like Baranoff and the rest of the ones that we can hardly remember, they suffer with an old infrastructure. I guess that's what I'm saying. And I have the feeling that ULA may end up in the same category. ULA, you may know, was nothing more than taking McDonnell Douglas, Martin Marietta, General Dynamics, Convair, all of the things that went into being all the Delta rockets and all the Atlas
and the
rockets.
Thors and the
They all,
Right.
finally, the companies that owned them, which ended up after the consolidation being Boeing and Lockheed Martin, decided that they wanted to get out of that. You know, there wasn't any money in building the same old stuff and running those factories. ULA took it all over. So they've got all this old infrastructure. And while their CEO shows things very nicely for the next generation that they're launching, he's having trouble getting Jeff Bezos' Blue Origin to deliver on the very large rocket engine that they've been developing for many years and not succeeded yet. It's years behind now.
Yeah.
And I wouldn't be surprised ULA is kind of in third place, you know, in a sense, as long as Boeing, I shouldn't say Boeing, as long as you know, actually Musk is the main game right now.
Yeah.
And of course, there'll be a European Ariane capability, just because that's the European government program, basically.
Right.
And India and Japan and others. But sorting out the large launch vehicle stuff in the US has really kind of happened. And if Musk and SpaceX succeed with the Starship, which if he keeps his forecast of launching it this year will be really impressive, but even if it's next year, I mean, that's moving still at the light speed that they've been able to do so far compared to Boeing. I mean, Boeing is an embarrassment to me in terms of the building of the space launch system. The space launch system is just, it's basically, it's the politicians' job creating answer to a large boost vehicle. And I still think there's a chance, even though NASA just rolled out the first of them, and it's supposed to launch within months. When you're talking about a multi-billion-dollar launch vehicle, that's so far unaffordable compared to what Musk is doing. I'm not sure how it survives, unless it becomes the U.S. government's program, like France and the Europeans have the Ariane.
Right.
Sometimes the government just keeps propping up the competitors, and I don't know about you guys, but I've worked for companies that were probably the beneficiaries of that, so you don't mind it sometimes.
Okay. Thank you.
But the small companies, there are just all kinds of people that are developing new approaches to rocket engines and trying out new fuels with them, and they're all so far in the small sat category, but you're going to hear more about them, not less, in the next few years, I think.
Mm-hmm. Thanks.
Thanks. Other questions? John, did you have your hand up? Asking a question.
Hey guys, I really appreciate your attention on a Friday night. That's tough to give up that time, so I hope you found that of interest.
Yeah, this was great. All right. So
anybody else?
Yeah, any other questions?
Thank you very much.
Thank you very, very much. Very well done. Thanks.
You're all welcome.
Thank you.
I enjoyed it. Thanks a lot.
Thanks again, John.
Yep, have a good weekend, and go Villanova. See you guys.
All right, take care, John. Thanks again for coming.
Thank you very much.
All right, so I guess that brings this meeting to a close. So if folks want to hang out, they're welcome to, but otherwise we will declare this meeting closed, and we will see you in Radnor next